Another important issue we often face is the synchronizing of a blockchain. Please welcome Hristov from Quanterall, who is going to shed some light on how that works.
So, hello there. My name is Hristov, and I'm an Elixir developer at Quanterall. Today, I'm gonna talk a little bit about synchronizing the blockchain. So, the most basic building block in any blockchain is a ledger to keep the track of the state transitions. If all we care about is keeping this ledger on our local machine, then there's nothing much we have to do, but things tend to be much more interesting when there are more parties involved. When there are more parties involved, a distributed ledger is needed, and for this we need to communicate with other nodes and exchange information about the state transitions in order to synchronize with their local ledger. In this presentation, I will try to explain how a set of peers can exchange this kind of information, even if they don't trust each other or even they can be malicious. With this in mind, we have to come up with an idea and with a protocol which is not hampering the speed of the network, but it keeps it secure. First, we're going to talk about the transport protocol. Transport protocol, the initial implementation of it, is using TCP connections. All communication will be encrypted and authenticated to ensure both confidentiality and integrity, which prevent adversaries from interfering the protocol and changing it. This de-anonymize the node to some degree. For transport protocol, we are going to use noise protocol with the exact name being noise XK25519 Chachapoli Blake 2B. Georgi explained about this just a few minutes ago, but let's go over it again. XK stands for the handshakes. The DH is over the curve of 25519. The Chachapoli stands for the symmetric encryption, and the Blake 2B is our hash function. So, yeah, everyone has a curve 25519 key pair for peer-to-peer communication. The bootstrapping of the peers is done by having a set of Aeternity trusted addresses in the node configuration. So for the bootstrapping, before any node can start the process of downloading the blockchain, it needs to discover suitable neighbors, which are part of the peer-to-peer network. We have two ways of bootstrapping this process. The first one is to have a central service which hands out an initial set of peers, for example, via DNS lookup. And the second one is to rely on hard-coded set of peers or neighbors, which are in the configuration files. Both of these options have advantages and disadvantages. The first, with the DNS lookup, the advantage is you can rotate easily the set of peers, but it is fairly centralized. And the other one, to have it in the configuration files, it's not that easy to rotate the initial set of peers because this requires an update to the node package software. Okay. And now for the neighbor selection. After a node has been bootstrapped, it should try to keep fairly stable neighborhood and thus try to persist peers across restarts. to describe the selection process, we need to come up with strategies for neighbor replacement and a preference function which can choose a peer out of a set. Choosing the selection strategy is very important because it influences the node degree, which in turn controls the resilience of the network and the message overhead. Now I'm going to talk about the routing in our protocol. As Michal explained earlier, we are going to use the Bitcoin NG protocol. In Ethereum or Bitcoin, this protocol is not of such an interest because nobody knows who is gonna mine the next block. And the peer just hands out the transaction broadcasted to everybody and hopes the winning miner to pick it up. But this protocol, Bitcoin NG, can be in interest of the users who have tight timing requirements or just want improved user experience because of the decreased latency, and they can just send their transaction they want to make to the current leader. And this way you can't flood the network. So here is a small diagram of the Bitcoin NG protocol. The blue squares are the key blocks. They have no content, and they're just used for leader election. And the circles are the micro blocks. They are consist of transactions, so only content, and they have no contention. So the incentives. There's a body of research proving that Nakamoto-style consensus, it might be in miners' interest not to share the mined block right at the moment it is mined, which can damage our network. So yeah, that is bad for the network. And for the block and transaction synchronization, so this is the interesting part, actually. At startup, after discovering at least one peer, the node will synchronize the chain and the current list of unconfirmed transactions. Synchronizing the chain is actually a big task, and the node will utilize all its connected peers to fetch blocks and transactions. Fetching the transaction from other peers is not so big task, so the node will just take one of the peers and fill up only the missing transactions. So here's an example. How does the sync process work? Let's say node 1 wants to sync with node 2. The first thing after they to each other is to send a ping object. And the ping object is consisted of this. This is the ping object is actually a map with keys: genesis hash, best hash, difficulty, peers, share, and source. And its respective values, where the genesis hash is actually the hash of the first block, which is hard-coded, you know. The best hash is actually the top block hash of the header. The difficulty is calculated from the target, which controls the mining rate. You hand out your peers, your peers you're connected to. The share is an integer, which represents how many peers do you want to share with him. And the source is the URI of yourself. So what is the workflow in the sync? The first our genesis hash means remote genesis hash, the hash of the node we want to sync to. First, if your genesis hash and his genesis hash are not equal, you should abort the sync and block this peer to be sure you don't have any communication further on. Because it means you didn't start at one network. But if they are equal, then the node with smaller difficulty target will fetch the remote top header and fill all the headers he's missing, not the whole blocks, only the headers, until he has a continuous chain. Then both of the nodes ask their own chain for a list of hashes representing the missing blocks. And after that is done, they send the blocks each other. And then both nodes request all transactions in the mempool of the other node. If any of these steps fail, it should lead to abort. So to sum up with the block transaction propagation, the first thing is to announce the new transaction and block to the peers. Then a peer asks for data if they don't have it. The good thing and the thing which is making the syncing fast is actually you don't have to send the full block with all the transactions. You just send the header first. So for the proof of work puzzle, this is an option in our sync, and it is utilized when somebody is under attack of an Eclipse attack or a denial of service attack. You can ask to the peer which you think is malicious to solve a proof of work puzzle, just to verify he is not malicious. Yeah, this can be done both offline or online, each of which have their own merits. If you want to compute the proof of work puzzle offline, this opens up an attack, but gives the opportunity of the resource-constrained nodes to easily participate in the network. But as I said, this opens up for an attacks. For example, a faster node can make 2 or 3 or 4 solutions while you have just one to this proof of work puzzle. And when you connect to him, after he sends you a nonce, you can just take his static key used in the handshake, concatenate it with the nonce, and yeah, it's a valid solution, but actually it's not. So how is the workflow of the proof of work puzzle decided to be? First, the initiator connects to a node. The responder sends a challenge. The initiator disconnects. Then the initiator computes the solution. And lastly, initiator connects again and provides solution. But there could be a problem if the proof of work puzzle is overly difficult, which means that not many of the nodes can easily find a solution to such a puzzle. And this may cause nodes to leave the network. Now for the reputation system. Actually, we are using very simple reputation system. The reputation system is only used to punish the nodes for misbehaving or sharing garbage. The garbage can be invalid transactions or invalid blocks in our case. So your reputation is actually local, and it has a threshold. When you misbehave, you lose reputation. For example, if you reach 0, then the other node might punish you and block you for 24 hours or for how long they decide to. So what configurables do we have in our implementation? These are the proof of work targets, which is for the mining rate, the proof of work wait timeout, the listener interface, the ports, the connection timeout, the overall connections we can make, the incoming connections, the gossip pool size, and the blacklist and the whitelist for the peers. So, about the threat model. Every threat model comes with assumptions that are out of scope and not in the attack vectors. The first one is our blockchain ledger is using Nakamoto style, which means do not have any miner or participant who have more of 25% of the mining power, which will keep our ledger consistent. The second one is there's no secret transmission using the cryptographic keys or controlling coins. So there are no secret transmission, but we use the keys, the cryptographic keys, as Georgi explained. And we assume no physical threats to our implementation of the sync. So for the transport, as I said, we are using the noise transport protocol. And things like authenticating and encrypting the information takes off the eavesdropping or man-in-the-middle attack. But denial of service attack can be mounted at different layers. For example, either at protocol or the node level, which is slowing down block propagation, which increases the risk of forks and makes selfish mining even more profitable. And resource exhaustion for a single node by using up all connections and filling up the RAM. Security-wise, it can cause an Eclipse attack, which leads to double spending. And it is possible to see the other peer information without encryption. So this should be considered as a threat. So I've already said about the Eclipse attacks, but I'm going to try to explain simple what an Eclipse attack is. So let's say this is the targeted node. The red one is the malicious node, and these are honest nodes. As you can see, the targeted node is surrounded by malicious nodes. So he has no way of knowing that they are malicious because all of his peers are malicious. And they're isolating him, as well as the honest nodes doesn't know of that there is a targeted node. This node, for example, has one malicious node and one honest node. So he can make the difference and to understand which node is malicious, but this one can't. So if there is a union between these malicious nodes, they can split up the network into smaller parts. And when there are smaller parts in the network, they are more easily controlled. So in short, this is an Eclipse attack. We have dimensions to be tuned because our implementation is still initial. For example, the network bandwidth usage, the network latency for transaction block propagation, the reliability, and the memory or CPU usage. But as it is in the most cases, we can't have all of it at the same time. Ideally, our protocol has the knobs to let the user configure what they want. For example, if you're running on a mobile device, you may want to reduce your network bandwidth in cost of increased latency, or on the other side of the spectrum, if you want increased network bandwidth, this leads to decrease in latency and increased CPU usage. Okay, that's it for me. Do you have any questions? Okay, thank you.